In this video, we talk about moving average processes. So moving average process is that you have an input random process and the output can be calculated as a moving average of the input. So you don't need to have any feedback. So it's a kind of like it is produced by an FIR filter, finite impulse response filter. So in that case, so the input is IN and then the output is XN, and then this is given to a delay unit Z minus 1, another delay Z minus 1, etc. So here you get I of N minus 1, I of N minus 2, etc. and then you get I of N minus M. How many delay units we need? M. So you multiply the first one by B0, next one by B1, and last one by BM, and then summation of all of these guys produces X of N. So basically your random process X of N, so this is your random process that you have, is produced by whitening noise, white noise, and a moving average of this white noise. So these different samples of I of N minus 1, and so on, these guys are uncorrelated samples. And then the objective of a moving average random process is that you represent X of N by using these parameters. These are the parameters B0 up to Bm and the random process I of N. Variance of I of N is assumed here to be equal to 1. So the Z transform of the tap delay line filter, IR filter, is given by this expression, and then you can see that X of Z, the power spectral density in Z domain, is equal to L of Z, and then L conjugate of Z minus 1 conjugate, or L of Z minus 1, provided that all BI's are real, because RII of let's say M is equal to delta of M, and SII of Z is equal to 1. So you multiply these by L of Z and L of Z conjugate Z inverse, then you get this. Now, so if you use this equation and multiply both sides of this equation by X of N conjugate and take expected value, you immediately get this expression. If you multiply this expression this time by X of N minus 1 and then take the expected value, then you get this equation, and so on. If you multiply by X of N minus M and take expected value, you get. So you get, it is assumed that these guys are known, and then these set of B0, B1, B2, etc. are unknown. Obviously, if you have here M plus 1 parameters, and here you have also M plus 1 equations. So the number of unknowns and equations are equal, so basically you should be able to solve it. But the challenge is that these set of equations here are heavily nonlinear, and solving them is not an easy problem. So we cannot solve it. And this is why moving average random processes, they don't have very many applications. They have application only if M is equal 1, 2. For larger values of M, the hassle to calculate and solve this one is not trivial, because these nonlinear equations quite often they have multiple solutions, and then you have to find all of them and see which one is the real optimal one. And the order of the computational cost is very prohibitive to make this application. So it's hard to solve, and then this is why there is not very many applications. So there are other reasons why ARM is heavily used in many applications, such as speech or image processing. They are used to compress this and that, but for moving averages, they are not.